All right, so we talked a little bit last week, and I think I promised you your exams today. I shouldn't make promises that I don't have 100% control over. So I have your exams back, and I have the short answer portions graded. I just got them this morning, the multiple choice. I don't have the software, so I have to rely on someone else to do it. They're new, and they've taken a little bit more extra time than usual. So I will have those to you. I promise this time. I will definitely have them Wednesday to hand back. You should see your grades either pop up this afternoon on Canvas or sometime tomorrow. I've got several classes that I've got them all back at once, even though they were given to them at several different times last week. So I thought that was staggered, but apparently they pushed it all off and then realized I didn't know what they were doing. So we will we'll go over those a little more in detail on Wednesday. Like I said, from the short answer, it looks pretty good. I was trying to look at it between classes earlier, and the multiple choice looked pretty good as well. So I think the average wound up being pretty high, but I don't want to say anything without sitting down and looking at the data. In terms of homeworks, I will probably get up tomorrow a Connect and an Excel homework. We will not have worked through the Excel at all, but today we won't get to it. I just want to get them up there. The due date will be a couple weeks in advance. I want to get them up there so you can start chipping away at them as we start working through things the next couple weeks. Okay. Anything else I want to say? Any questions for me before we kind of jump into get going here again? Okay. So hopefully you see some up here. You either print it off or you're able to pull up that Z table. We'll kind of start using that today and kind of from here on out. We left off thinking about, we have a normally distributed variable. We can convert that into a standard normal distribution. And then once we have a standard normal distribution, what was the unique properties of that? We remember a standard normal distribution had a mean of 0 and a variance of 1, which coincidentally, right, if we take the square root of the variance, the square root of 1 is also 1, so the standard deviation ends up being 1 as well. So once we have that, someone's already done all the integration for us, right? If we want to find the probability that we're in between two values here, we don't have to integrate this function because someone's already done the standard normal distribution integration for us. Okay. So what happens if we start out with a variable that's not normally distributed? We kind of have the general setup, but the steps are going to be, where did I put this? Here it is. If I want to know the probability that I'm in between two values, we'll call it A and B. Well, I'm first going to convert my normally distributed variable into a standard normal distribution by calculating these z-scores. So if we remember, how do we calculate these z-scores? I said I would take whatever x value I'm interested in, subtract, remember, I showed you a little small data set example, subtract the mean and divide by standard deviation. These z-scores then told me the number of standard deviations away from the mean that this value was, or this x value. So if I'm thinking about, I've got two values A and B, and I want to know the probability that I'm in between those values, I want the area under the curve. So what I'm going to do is I'm going to convert those values into z-scores, and then use those z-scores, right? Because the table, I can look up that z-score. It'll tell me the area to the left of that z-score for A. I look up the z-score for B. The table will tell me the area to the left of that z-score. I could then take the smaller area, subtract it from the larger area, and I'm left with what I want in between. I have another visual up in the slides of that. So we convert it. We then calculate the z-scores for our two values. We're interested in finding the probability of being in between. Think about that region is. I add this step. I just always think it's easier to have a visual in front of you. In fact, the podcast I mentioned too, this whole thing was about, this is a British woman. She said the way to teach maths, I guess that's how they call mathematics. The way to teach maths is to always have a visual. So I try to give you guys visuals because I do think that helps, but it also helps you as you're working through them to create your own. We'll then look up those z values in our table, find the relevant probabilities, and then sometimes we have a little bit of work to do, right? In this example, I said, we could find the probability that we're less than this z-score from the table, find the probability we're less than this z-score. We can then subtract this smaller area from the larger area, and we're left with what's in between. So that's step 4. that kind of, we might have a little bit of like simple mathematics to do. And that step's always easier if you have a visual as well, I think. Okay. That's kind of where we left off, kind of wrapping it all up and putting it in kind of a step-by-step form. So let's work through some actual problems. So let's say I want to know the probability that I see some random variable x take on the values in between 10 and 15. So this one doesn't have a lot of context, maybe not the most interesting. It'll be the first one that we actually work through together. Right? So we just want to have some numbers to work with. Let's say this original variable x started out and it was normally distributed and it had a mean of 5 and a variance of 25. So anytime I see that I've got something normally distributed, I should know I can draw this out. Right? Now draw this bell curve. It's got a mean of 5. It's got a variance of 25. If the variance is 25, what's my standard deviation? Yeah, it's just the square root of my variance. So it also ends up being 5. Okay. So I know that the first step is going to be that I need to turn the values I'm interested in, right? The probability in between 10 and 15. I need to turn these into z-scores. Any questions up to this point on the setup? So before I get too far into this, what do I know this probability has to be less than? And don't say 1. We always know probability is less than 1. What other value do I know this probability has to be less than? I think you said it. Did someone mutter something over here? 0.5? Okay. Why does it have to be less than 0.5? If I look at the mean, I know that there's 0.5 to either side of it, right? 50% of the data or outcomes on either side. Well, I want something that's much smaller than half of this distribution, so I know it's going to be less than 0.5. Okay. And actually, let me make sure. I think everyone's here today. Okay, I was going to say, let me just make sure I hit the record button on that. So I know it has to be less than 0.5, but other than that, I can't really say. Right? I don't really know the exact value. So I'm going to work through this, right? So I'm going to turn this into a z-score, this value of 15, right? So I'll take that x value I'm interested in, 15. Got the equation over there. I'll subtract the mean. Well, the mean was 5. And I'll divide by my standard deviation, which was also 5. Okay. So I end up with a z-score of 2. Why could I have done that without really writing out that formula? I made the numbers easy here because remember that z-score tells us how many standard deviations away our x value is from the mean. How far away is 15 from that mean of 5? 10. Right? Well, what's the standard deviation? 5. So being 10 away is being 2 standard deviations away. Right? How many standard deviations away is 10 from the mean? 1. So without even doing the calculation here, the z-score for 10 should just be 1. Because the z-score reflects how many standard deviations away from the mean are. Away from the mean that we are. Which, even if we do the math, we'll get, oh yeah, we were 2 standard deviations away. We're 1 standard deviation away. Any questions on that? Now, if I don't choose really nice and easy numbers, like it's not as easy, right? I'm gonna have to probably use that formula for the z-score. But now it's just a matter of, I can look up that z-score of 1 on my table. I can look up that z-score of 1 on my table. There we go. Right. I can look up that z-score of 2. I want just what's in between, subtract the smaller one from the large one, and I'll be left with kind of just what's in between those 2 values. Okay. Think about it this way. What I'm really doing is, what's the probability that I'm less than or equal to 15? Subtract out the probability that I'm less than or equal to 10. Well, now the only values I'd be left with are the values in between 10 and 15, which is originally what I want. Okay. Any questions on that? So this is where you've got in front of you, probably a little bit easier to see. Right, I'll look at my standard normal table. I'm looking at positive z-scores. So I'm going to go down here. Now, if I'm looking up a z-score of something like 1, that's the same as 1.00, right? So I go 1.00, the probability of seeing that z-score or anything below it is 0.8413. So, I'll get rid of this and show you a slightly different one. So we just found this was 0.8413. Right? Probably have seen that z-score of 1 or anything below it. I then look up 2.00, and the area to the left of that, 0.99, nope, not 99, 9772. So if I want the probability of being in between these two, subtract that smaller probability from the larger one, and I'm done. So I think I've got that on the slides as well, but just different way of seeing it, right? So there we go. I kind of used that shaded blue area representing the probability I'm less than 2. The bricked area is the probability I'm less than 1. So I'm just going to find the difference between those two areas, and I'll be left with what is just in light blue, right, where they don't overlap. Okay. So these are the probabilities that we found from the table. And sure enough, it's less than 0.5. Right? So we know we didn't make any egregious mistake here. Any questions on this? So I think one thing we can kind of relate this to that we've already talked about. When I'm looking at the difference in between like this entire light blue area and just the brick area, it's almost like I'm subtracting out the intersection, right? So I mean, it's not exactly the same as what we're doing with unions, but it's kind of a similar idea where we're subtracting out that the intersection just to get the area that we want. That's not too bad. So we'll do some Indiana weather examples because I don't know, the weather's always fun. So let's say I have this data set. It's got Indiana weather all the way back to 1895. Right? And I've got, every single month and every year, I have what it is. I can calculate in Excel what the average rainfall is in Indiana. And I can actually break it down by month as well. Right, so I can find just the average June rainfall, just the average August rainfall. I've also got temperature data, which we'll play around with a little bit as well. But what ends up being true is if I graph this out, and I think by the end of class today, I'll show you in Excel, I have this data. If you create like a probability distribution where you can kind of look at just creating like a histogram, it looks pretty close to a normal distribution. So we've got, a normally distributed variable, we have the mean, we can calculate the variance, but we can start to solve problems like this. Well, what's the probability next month I see rain be in between 2 and 3 inches? Which, like, depending on what industry or sector I'm in, that might be very relevant, especially if I'm in agriculture. Right? That seems like something that would be really good for me. Okay? So here's kind of the rainfall overall. I didn't look at one specific month here. That's why you get some kind of weird things happening here in the tail. But if I was to break this down month by month, you see that monthly rainfall, like just June's rainfall and just October's rainfall, is even more of a normal distribution. But even here, looking across all months, pretty similar, right? Pretty similar to a normal distribution. So kind of the motivating example originally for me was in 2012, right? Indiana went through this severe drought, right? So this was like, I don't know who put this out, some government agency where you can kind of see like all these different counties. We're going through like extreme droughts, right? There wasn't a lot of rainfall. So how unlikely was that year, right? Or said differently, how likely is it we see a year with that little rainfall again, right? Let me do this next year. Well, you can kind of see even visually that 2020 drought. Yeah, there's cyclicality to weather, but kind of see here, February and June, rainfall always spikes. In 2010, February to June, rainfall spikes. 2011, February to June, rainfall spikes. 2012, February to June, not only did it not spike, it actually remained lower than kind of other months. Right? So this is pretty unlikely event, and we can actually figure out how unlikely it was based off of historic data. Right? So if I look at monthly rainfall in Indiana, I see that the average rainfall is 3.4 inches, and the variance, remember when we write this out, we always kind of write out this variable is normally distributed with this mean and this variance. What's the probability that we see monthly rainfall be less than 1.3 inches, which is what it in fact was in 2012. So, you get a visual for this. This is probably easier than the one that we just did, even though the numbers might be a little bit more complex, not as nice. So I've got rainfall here. And I know that usually monthly rainfall is normally distributed. So what, 3.4 was my mean? My variance was 2.57. And I want to know what's the probability that I saw 1.3 inches of average monthly rainfall or less. So what's my first step? Yeah. That's a good step, right? I don't have to, and I'll show you how I don't have to, but I want to find this standard deviation. I don't know what this works out to be. 1.68.
Oh, 3.
Oh, okay. So we're down to that second decimal. So I could do that. It makes my life a little bit easier in the next step, because the next step is I need to convert this value that I'm interested in into a z-score. I'm still looking for the probability I am less than or equal to that z-score. If I did turn the mean into a z-score, what should that mean have a z-score of? Yeah, the mean is 0 standard deviations away from the mean. So it's always going to have a z-score of 0. Now here, I remember my z-score equation. I'm going to take the x value I'm interested in. I'm going to subtract that mean. And I'm going to divide by my standard deviation. So I would agree, calculating your standard deviation ahead of time is a good first step. But what I could also do here is just put into my denominator the square root of the variance. I know that that would represent whatever that standard deviation value is. So if I want to break it down step by step, I can probably helpful. But if I want to, I can kind of wrap it all up into that same equation. So first of all, what do I know my z-score, the sign is going to be? If I see something below the mean, well, then it's going to be a certain number of standard deviations below the mean, which would be a negative z-score. So if I get a positive value, I know I've made a mistake here. So I plug this in, what do I actually end up with? Negative 1.31. It just so happens that the z-score is close to that x value. Right? It doesn't have to be the same. Really, the reason why is because that standard deviation is getting close to 1. Right? And that's the only reason why we. Sorry, not that it's close to 1. It's close to the difference between the mean and the value I'm looking at, right? 1.6, below 3.4 is getting close to that value. So it just happens to be pretty similar. It could have been, in any other example, any of the numbers I have, my x value could be wildly different than the z-score, right? Especially if I'm looking at something like income. Well, my income is going to be in the thousands, so for sure my income is going to look nothing like my z-score is. So now, what's my next step? Look it up in the table. So if I go to negative 1.31, what does the table tell me? 0.0951. So the probability we saw rainfall as low as we did in 2012 or something even lower, it's only about a 9% chance or 9.5% chance. So unlikely, but really not the most unlikely, right? And that's because even though we were pretty far away from that mean, 2 inches below average monthly rainfall, our standard deviation is pretty big. I mean, relative, right? Being 2 inches below, well, that's almost a standard deviation. It's not that crazy. So just over a standard deviation, right? 1.3 standard deviations. Questions on this? So now we look it up, we get 0.05. Number 4 here, we don't have any transformation. All right, that's the area we wanted. We wanted the area to the left. What if I had asked you what's the probability we saw more than that 1.3 inches of rainfall? Everything will be exactly the same, except for you're looking for the area to the right. So all I would have to do is 1 minus that. Okay. And that, then I would have actually something to do for that 4th step, right? But if I'm looking for the area to the left of a certain value, my 4th step is essentially non-existent. I don't have to do any transformation. I found from the table exactly what I want. Any questions on this? All right, so give you a chance to kind of work on one. So let's say we're looking at September rainfall. And this was last September. This was I tried to use relevant examples, but last September was too crazy for me to switch this value. So last September, any of you remember what last week was like? I was trying to forget. But September, we only got like half an inch of rainfall, so 0.47 inches of rainfall last year in the year. The average is 3.25. The variance on September rainfall is 2.37. Right? So what's the probability that we saw rainfall as low as we did last year, or something even lower? Said differently, the probability we saw 0.47 inches or less. So using that mean, using that variance, right? We should be able to do a similar thing to the problem we just did. Using that table, we should be able to find the probability we saw 0.47 inches of rainfall or less. So I'll give you a couple minutes to work on this one. Feel free to work with the people next to or on you. I said feel free to. I actually would highly encourage it. Another theme in the podcast I listen to. Collaboration is great in mathematics. Oh, hell if I gave you answers, huh? Why are my answers not showing up? Give me 1 second. Did I delete them? Well, work on this and we'll talk about it. Respond with any A through D, whatever letter you like today. Everyone will get credit for this one, but I want you to take a little bit of time to work through it, and then we'll kind of address any issues you ran into. Okay, actually. If you've worked on it, don't just respond with whatever letter you want. I'll come up with a real quick eye clicker question. Okay. So let's say these were the possible answers. Okay. So if these were the 4 possible answers I gave you, you should be able to not work through the problem and know which of these has to be the correct probability. Okay. So look at these answers, right? And you should know which of them has to be the correct. Now, they don't line up with what the actual answer is, but assuming these are the only answers you were given, you wouldn't have to work through it, and you know only one of these could have been the possible right answer. Okay. So if you drew it out, you should be able to rule out all but one of these pretty much.
You're only like 1 in 1,000.
Really?
Yeah.
Man, I'm good. No, I totally just came up with that value. But yeah, so respond with which one is the only one that could have been the correct answer. Okay. All right. It's your best guess in here if you haven't gotten an answer in. Should be 13 of us, right? Or 14. So one of you still needs to get an answer in. All right, I'm gonna close it out. All right, we're good. So which one, if I gave you only these four, has to be the correct one? A. Right? So why? Yeah.
Because B and D are about 0.5, C is like
Yeah, right. So if I have a mean of what, 3.25? And I want to know the probability of being less than 4.7. The area to the left and the right of the mean is 0.5. So right away, I can rule out B and D. But then if I just stop and take a closer look at it, if I wanted the probability to be 0.4999, what would have to be true about the X value? Be really, really close to that mean. I have a value that's how many standard deviations away from the mean. The standard deviation here, once again, is going to be probably 1.34-ish, somewhere around there. So I'm like several standard deviations away. I kind of said last class, being more than 2 standard deviations away is pretty far away, right? So right away, I know that I'm pretty far away from that mean. That area should be relatively small, right? A lot closer to 0 than it will be to 0.5. Okay. It's not the perfect drawings, but we went over it kind of. But does everyone understand why we could kind of rule those out there? Now, I should be careful because just because the value I see isn't close to my mean doesn't necessarily mean I couldn't see 0.4999. So let's assume I was thinking about something like seeing 1.3, and maybe I drew it like this, but this wouldn't be to scale if instead my standard deviation was something like 30, right? Because then, even though I'm like 2 inches, which doesn't make sense in the context of this example, but go with me for a second. Even though I was 2 inches below the mean, that was like a small fraction of the standard deviation, right? So even if I see something that's a pretty far value amount of that X variable from the mean, like in income, when I look at income, I'm seeing things that are thousands of dollars away from the mean. But the standard deviation on income is like in the tens of thousands of dollars. So don't just look at the X value, right? Think about, okay, I'm 2 units away from the mean, but it's not how many units away, it's how many standard deviations away, right? And being 2 away from the mean, right? If the standard deviation is 30, I'm what, 15th of a standard deviation away. It's not very far away from me. So if the variance of the standard deviation was high enough, then technically 0.4999 is a theoretically possible value. But with a variance as low as 2.37, being 2 away is pretty good number of standard deviations. In fact, if you work through it, how many standard deviations away from the mean was 0.47? And why do you know it's 1.8? Because that was your z-score, right? Remember, you're calculating that z-score, that's telling you how many standard deviations away you are. Right? So before you even look it up in the table, kind of in the back of your mind, keep in the back of your mind, like, if I start to see things that get close to 2 standard deviations away, that's pretty far, right? And that's what your z-score tells you. Okay? I think I got way too excited about that. But are we all kind of okay with this? I think I've got, we look it up, negative 1.81. You looked it up in your table. The area to the left of negative 1.81 is about 0.035. And then we don't have any transformation to do there, right? Because that was originally what we wanted. Any other questions before we kind of move on here? All right. So I think the next one, I start to work with this temperature variable. Once again, follows a normal distribution. We can break it down by month. So maybe I break this down to June temperature and find the average and the variance. Notice there's a little bit more variation in temperature, which makes sense. There's just a wider range of values we see with temperature versus rainfall. And we could do several months if we wanted to. So let's say we went through one where I got average June temperature is 70.75, 6.3 is the variance. I know it's normally distributed. What's the probability that this next June, I see the average be 71.4 or greater? Right? So once again, if I draw this out, I can probably put some limits on this right away. Okay? So I said, you know, it's not just how far away we are in the number of units we are from that mean, it's how many standard deviations we are. So if I'm thinking about 71.4, and I've got a mean of what, 70.75? I want the probability I see that value or greater. Okay? So when I turn this into a z-score, I should have a z-score that is negative or positive? Positive, right? It's a certain number of standard deviations above my mean. Okay? So when I convert this into a z-score, right, and here we have what? Temperature. It should have a positive value. Now, if I'm thinking about the area to the right of that, automatically I know that probability has to be less than what value? What's the probability I see something above 70.75? Yeah, right? The mean, the area to the right is 0.5. So the area to the right of 71.4, or the area to the right of any value above the mean, has to be less than 0.5. So right away, I can rule out what? A and actually B and C there, right? A and D are still possible answers. What's my standard deviation here? So 6.3 is my variance. So my standard deviation would just be square root of that, right? Or somewhere in between 2.5-ish. Is it exactly 2.5? Okay, 2.51. So how many standard deviations about am I away from the mean here? I don't know, definitely less than one. Looks like less than a half here, right? So I actually have a value that's relatively close to the mean. So if I'm guessing here between A and D, which one probably makes a little bit more sense for me to go with? If I'm less than half a standard deviation away from the mean, then this area is going to actually be pretty close to 0.5, or at least closer to 0.5 than it would be to 0. In order for it to be closer to 0, I'd have to see something that's probably more than a standard deviation away. Now, I can't say exactly. Like if I gave you, 0.39 and 0.33, well, I don't know. Right? Like we're starting to get where we can't really make a very well-educated guess between those options. But if I'm between A and D here, I'm probably going to go with A. Right? So if I turn this into a z-score, right, I take that x value of 71.4, I subtract that mean, and I divide by my standard deviation. What do I get there? Anybody come up with that now? 0.26. 0.26. So yeah, way less than half a standard deviation, right? Almost a fourth. Okay. So if I looked at 0.226 up in the table, right, just to kind of show you an example of that, just to make sure we're all comfortable with it. I look up 0.2, go over to 0.26, 0.6026, right? So that's the answer, right? No. I want the probability I'm greater than that value. So what I actually want, and this is where, when you're drawing out that transformation, I think it's always helpful to, whatever area I shaded in for that original x variable, make sure right away I shade that area in when I'm thinking about my standard normal distribution as well. That way I remember, oh yeah, this is what I'm looking for. So to find that, I would actually have to take 1 minus the probability I'm to the left of that z-score. And that works out to be that 0.39, what, 74? Any questions on that? No? Okay with that one? All right, we got about 15 minutes. Let me think what I want to do here. You guys seem like you're really getting this. Am I like, I'm not far off on that, right? You guys are understanding this pretty well? Okay. I was gonna say, if I'm making it up, let me know, but it seems like you guys are doing pretty good. So I had this one because I thought it was kind of interesting. like I said, I always try to make it relevant. I won't make you work through this one, but if you want some additional practice on your own, we just gave some different numbers here. I worked with some February data because 2017, so it's starting to get a little bit far off in the past now, but close enough we can remember. It was like an exceptionally warm February. The average temperature was 42.8, and I was like, in my head was like, man, this has got to be really unlikely, but it was just warm. I was like, wait, I'm teaching like normal distribution stuff. Like I know temperature is normally distributed. I can figure this out. So I went to that data. This is where this all came from, like this idea of Indiana weather. You can actually find the mean temperature in February in Indiana is actually pretty low, a lot lower than I would have expected. But there's a huge variance on it, right? Compared to these months, we were talking about like variance in temperatures like 6 for June, 6 degrees. It's 26 in February, right? So I was like, oh, it was pretty far, it's a pretty big gap, but also that variance is pretty large, right? But the square root of that, right, the standard deviation is only like 5. So it was still quite a few standard deviations away, right? More than 2 standard deviations, 2.7, which the probability of seeing something that far above the mean or greater was actually like 0.3%, right? Or 0.003. So anytime you're curious in this stuff, like if you're a nerd, you can go out and grab the data and like figure it out, right? So yeah, and I was very excited about this. So multiple exclamation points. So before we do the inverse, I'm just going to kind of show you a little bit, I think, and today, like 15 minutes or so, we'll do a little bit of work in Excel. So the inverse transformation, I think we'll probably end up saving that till Wednesday. I used to kind of go through a couple topics and then we would do a bunch of Excel work, but I think I like the idea better. I've been trying to use more is sprinkling Excel in. So under that in-class data folder, there should be an Indiana weather file up on Canvas. Okay, thank you for the affirmation. If I say something that's not true, let me know, okay? So if you open it up, it's got several tabs. I think, here I kind of built some of the stuff I showed you in the slides, just to kind of support that rainfall looks pretty normally distributed. Certain months start to look a little bit more skewed, but for the most part, I would say it's normally distributed. So let's go to, did I have one I left open? No, let's go to this temp normal one, okay? So here we've got this temp normal file. I've got different months. I'm gonna zoom in so we can see what's going on. Maybe 150. So I'm actually going to, I think I've got January here. So I'm gonna delete everything that's in here. I think we can actually build a little bit more. So let's do January, February, March. And then instead of typing all this in, I'm actually just going to copy these months here. And I'm going to paste them over. For right now, for the sake of what we're doing, if you're trying to work along, just delete what was there in terms of the months and the numbers. And if you really just want to, for now, just start with January. We're just going to work on January 1st. Okay. Everybody okay with that? All right. So if I want to find, as long as I assume for now that every month temperature is somewhat normally distributed, I can find the mean by using that average function, right? So I'll put equals average, I'll scroll over here, select that very first year I have data on for January, Control Shift, Command Shift on a Mac, hold those down and then hit the down arrow and actually go up one because I forgot that I had some data down here as well, okay? So we don't want to include this. This isn't like a temperature, right? This was for something else that this file was using. So I wanted to kind of make sure I showed you an example where we have an extra row that's not data. Because if I use that shortcut, it can't differentiate between the data set and then just these values that I had entered down in here for some other reason. The other reason was I was identifying like what month it was, right? January was month 1. So be careful when you're using that shortcut that it's just selecting the data because it'll go to the last cell that has a value in it, okay? So one way we can do that, so if I go back up to the top here, oh, I have to show you again. Give me 1 second. So if I click on that cell, Control Shift, I hit the down arrow. In order just to go back one, I'm still holding Control and Shift, and then hit the I let my finger off control, right? So control is like the thing that sends it down a bunch. Shift is just like if I wanted to select 2 cells or go over 1 cell. So taking my finger then off the control, I just hit the up arrow once. I'm gonna say that again. I'll show you a slightly different because I think I'm seeing some puzzled looks. So let's say I just wanted to go over 1 cell. I would hold shift and hit the over arrow, right? So when I'm holding shift, it only goes over or down 1 cell at a time. If I hold control and shift, well, then when I start using the arrows, it starts going over to the very last cell that has data in, okay? Well, I don't want to do that. So select on January, hold control and shift. Now when I hit the down arrow, that should send me to the very bottom. Well, now I'll let off of the control button, and now I can move around 1 cell at a time. So notice now when I'm using my up and down arrows, but I'm just holding shift, it's only going up and down 1 cell at a time. I guess probably, maybe if I don't want to deal with this, I could have just deleted those month identifiers. I don't even remember why they're originally there in the data, but I knew this was a good point where I could kind of show you that. Okay. So I hit enter, and I get kind of average January rainfall there, all right? I then go equals, I'm just going to find the, so I think here, we'll do the variance, right? We'll treat this as a sample because we don't have every year ever existed in Indiana, right? So go over. I could even use my mouse if I don't want to mess around with the shortcuts. And I could just select the variance of this January temperature variable, okay? Hit enter, it'll send me back to the cell. Here I could find the standard deviation 2 ways. I could use that built-in function, or if I've got the variance, I could just use the square root function, which was SQRT, right? So just take the square root of that variance. Anybody with me up to this point, or any questions here? Okay, so I've got kind of my variance, standard deviation, and my mean. Well, notice I have the data set up so that it goes month by month. So I actually can just copy this over and it will very quickly find, okay, well, yeah, now it's using the column for February and this one is using the column for June. And I quickly get the mean, variance, and standard deviation for each one of these months, okay? Any questions here? Just to mention, I think I have a few more years here. Let's see if that's the case. Yeah, I've got a few more years here than the values I was showing you in the slides. So that's why if you're trying to match this data set up to the slides, it'll be a little off because I have a couple more years of data in this file. Okay, I updated it. All right, so now that I've got all these values, I can start to do things like, okay, maybe in January, I look at that mean and I say, okay, well, what's the probability this January, the temperature is above freezing, right? So this X value, or just the values that I'm interested in finding the probability of being less than or greater than, or yes, maybe here we'll say, what's the probability that it's below freezing in January, right? Below 32, less than 32. Well, I could calculate my Z-score, right? That would be as easy as taking my X value, subtracting the mean I have up here, and then dividing by my standard deviation. Okay. So that would give me my Z-score. Now, here, if I could label these just so I can kind of remember what's where. So now that I've got my Z-score, instead of looking it up in the table myself, I can use a built-in function in Excel that basically, like it has like, well, okay, what it actually does is does the integration, but it's almost like it looks it up in the table for you. And its table isn't limited to 2 decimals, right? I always tell people like, sometimes I get the question, well, what if I want to look up a Z-score that goes out 3 decimals? Well, you'd need like a 3-dimensional, right, table that had the decimal point in the thousandths place on the other axis. And then, well, what about 4? Well, I can't even visualize what that table would look like. Basically, you'll have to do the integration, and Excel will do that for you. So that built-in formula is norm.s.dist, right? So basically, it's telling Excel, hey, use that standard normal distribution and look up the probability I see this z-score or anything below it, right? So I can look up this z-score. That's the first thing I tell it. And then for the sake of this class, I haven't dove into exactly what the 0 does, to be completely honest, because if this truly is cumulative here, so when I put a 1 in, it should find the probability of seeing that z-score, 0.86, or anything below it, right? If I put a 0 in to make it not cumulative, what should it return to me? 0. Remember, the probability of any one value should be 0. I think what it does, as far as I've explored it, I'm not as interested in exploring because it's not useful for the sake of what I want to do or what you guys want to do. I think it's taking like an infinitesimally small interval, like a really like an interval of 0.001, and then returning to the probability, right? But we're never going to use the non-cumulative aspect of this function. We're only going to exploit this function basically working the same way as the table and giving us that cumulative probability, okay? So we'll put comma 1 there. And then that's the only other thing it needs. And it basically would return that value that I would find in the table. All right. Any questions? Yeah. Yep. So all we're going to do, right? So when we're finding that z-score before, we're going to take the x value we're interested in, and this could change, right? I chose 32, but I could find the probability that it's less than 40, right? This January, or less than 60, which will probably be pretty close to 1, right? But really, x is just the value that we're choosing. And then I'll subtract that mean for that whatever variable I'm interested in, here, January temperature. And then I'll divide whatever that difference is by my standard deviation for that variable. Yeah. Any other questions on that one? Okay. So I could then, you know, if I would probably want to change this value, right? But I could copy this across and have different months here, right? So the probability that it's less than 32 in January is 0.8. The probability it's less than 32 in February is 0.64. Probability the average temperature is less than 32 in March, well, that probably starts to decline rapidly, right? Because March tends to be warmer. Well, and then notice once I start getting to like June, July, well, now the probability is essentially 0, right? The average temperature being 32 in July, I mean, just intuitively, that probability is probably 0, right? And sure enough, e to the negative 54, that means move the decimal point 54 places to the left. Yeah, we do get 0 probabilities. But because I have it set up this way, I could find the probability it's less than 32 in every single month. Right? And if I had had a little more foresight, I probably would have started this over one more column, so it'd be very easy to line up with what months were what. Here, they're like, you know, kind of one off, right? A little bit. Okay. Questions on that? So 2 minutes. I'll hold off on showing you that till next class. What if I wanted to do the probability that I see the z-score be above a certain value? Well, there, the only other step, I could still use that standard normal distribution function. I would just have to be subtracting it from 1, right? So that norm.s.dis function works the exact same way the tables do. And it always gives you the probability of seeing that z value or anything below it, the area to the left. So if you ever do want to find the probability of being above a certain z-score, you can still use that norm.s.dis. You're just going to have to subtract it from 1. Okay. So I could, you know, subtract all these from 1, and that would basically give me the probability that I see the average temperature be above 32, which once we start to get to these warmer months like June and July, that probability is so close to 1 that Excel doesn't even display it to us that it's in fact something slightly less. All right, so Wednesday, we will pick up here. We'll do a little more work in Excel. We'll kind of start to talk about the inverse transformation, look at how we do that in Excel, and then probably transition to sampling, okay? All right, we'll see you guys on Wednesday when I will, with 100% certainty, be returning your exams to you, okay?